For centuries, the standard model of scientific inquiry has relied on the measurement and observation of naturally occurring phenomena. This traditional, positivist model provides a clear framework for testing a hypothesis against established physical laws. But in information and communication technology, researchers hit an epistemological wall. The traditional methodology offers no path forward when the phenomenon researchers need to study does not exist yet. In the mid-20th century, Herbert Simon identified this friction. He argued that professional disciplines required a distinct approach, what he called a science of the artificial. Simon drew a boundary. A natural science studies how existing objects behave in nature. A design science studies how artificial constructs are built to interface with their specific environments to achieve a goal. Analyzing human-made IT systems forces researchers to abandon pure observation. To study the system, the investigator first has to invent the environment they want to analyze. We map disciplines along two axes. Vertical separates symbolic from real. Horizontal divides exploration from invention. The left is populated by analytic fields like chemistry. The right belongs to synthetic disciplines like architecture, where knowledge is accumulated by building artifacts and analyzing their performance. Yet a persistent skepticism exists regarding software and IT. There is an academic assumption that building an IT system is routine engineering, a practical application of known science rather than a discovery of new principles. Routine design happens in industry. Engineers minimize risk by applying known paradigms and standard practices to state-of-practice components. Design science research operates in the opposite direction. It seeks out theoretical vacuums. Researchers target the specific areas where no known solution exists to actively pursue missing knowledge. The rigor of this research comes from weaponizing intellectual risk, using the actual construction process to extract valid scientific theory. This diagram shows the design science research process model. It provides the structural scaffolding required to prove that constructing an IT artifact is rigorous, peer-reviewable research. The cycle begins with Phase 1. Awareness of a problem. An investigator identifies a theoretical gap, triggered by industry developments or cross-disciplinary observations lacking formal explanation. That leads directly to Phase 2, suggestion. This is a creative step, where the researcher envisions a novel configuration of existing or new elements, specifically designed to solve the identified problem. The cognitive mechanism driving this entire phase is abduction. Abduction is the non-algorithmic intellectual leap from raw curiosity about a phenomenon to the formulation of a tentative architectural design. Without this abductive leap to a tentative design, the problem remains unresearchable. Abduction is the required catalyst that initiates the science. Moving down the diagram, the tentative design enters Phase 3, development. Here, the proposed architecture is implemented into a working artifact. A distinct cognitive shift occurs at this stage. The researcher steps out of abductive reasoning and relies strictly on deduction to physically construct the system according to the design parameters. The actual implementation techniques used here can be entirely pedestrian. Building the artifact often relies on standard state-of-practice development tools. The physical coding and the manufacturing of the system do not need to be a breakthrough invention in their own right. The scientific novelty lives strictly within the theoretical architecture formulated during the design phase. The scientist's role is in the blueprint. The technician's role is in the execution. Following development is Phase 4, evaluation. This is the crucible where standard engineering diverges into formal science. In positivist research, evaluation is used to definitively confirm or kill a hypothesis. Design science treats early hypotheses as incomplete nomological networks, robust theoretical structures that demand continuous refinement, not immediate disposal. This continuous refinement is driven by a mechanism called circumscription. Circumscription is the deliberate discovery of constraint knowledge. Researchers achieve this by analyzing the exact contradictions between an artifact's expected theoretical performance and its actual behavior in the real world. When the artifact fails to behave as predicted, circumscription forces a hard loop back up to the suggestion phase. This drives new library research and forces specific architectural modifications. Anomalies and failures during evaluation are not project killers. They serve as the primary engine for generating theoretical constraints, making circumscription the true source of validity in design science. At the bottom of the diagram, the iterative loop reaches an exit condition in phase 5, conclusion. That exit condition is called satisficing. The researcher determines that the artifact performs well enough against the revised hypotheses to solve the problem, even if minor behavioral deviations still remain. With the physical build complete, the researcher executes 2 final cognitive steps, reflection and abstraction. The findings are actively segmented into firm knowledge, behaviors that can be repeatedly invoked, and loose ends, the remaining anomalies that are explicitly flagged to guide future research communities. Knowing precisely when to stop the iterative build loop is essential. It signals the necessary transition from active construction into the formalization of knowledge. This brings us to the final output of the entire process, and a common misunderstanding of the field. While software or algorithms are functional outputs, they are rarely the primary scholarly contribution of a DSR project. The peer-reviewed deliverable is the design theory, an abstract map of generalized know-how, constructs, and models extracted from the build. This theory provides the generalized blueprints that allow the wider academic community to reliably navigate this newly mapped theoretical space. Extracting this explicit design theory is the shield a researcher uses to defend their work against a skeptical, multi-paradigmatic academic environment. When exploring the frontier of information technology, rigorous building is rigorous learning. It is the process required to transform an engineered artifact into pure, generalizable science.